Now that we've learned significant figures, how to calculate significant figures, we need to talk about the reliability of these measurements and the vocabulary that we're going to need to use to compare and contrast different measurements to each other. So the first thing we need to talk about is something called precision and accuracy. Sometimes in normal talk, we kind of use them interchangeably, like they're kind of basically the same thing, but in science, they actually have very different meanings. Precision, well, let me start, excuse me. Accuracy refers to how close you are to the intended value. So if we're trying to get to a particular number, then if you are attaining that number, then you are accurate. If you're far off, you lack accuracy. So it's basically how close you are to a expected value. Precision, on the other hand, precision is only applicable if we have multiple measurements. So we don't just do an experiment once, we'll do an experiment many times, and that gives us more confidence in the results, right? Well, if we're getting a vast diversity of answers, then that's a problem because our precision is not very good. Precision refers to how reproducible our results are. How close are they to each other? Not necessarily to the expected or our desired value, but how close are they to each other? That's precision. Accuracy, again, is how close are you to the expected value. So in this particular example, we have some darts, just because this is, again, a precision sport. So the very top example, we have some purple darts. They're all thrown at a target. Ask yourself, is this precise? Is it accurate? Is it both? Or is it neither? So again, for accuracy, you would have to hit the intended target. And now again, in darts, that is typically going to be the bullseye. So did any of these purple darts hit the bullseye? Nope. Therefore, it is not accurate. The second question is, are they reproducible or are they all very similar? Now, the purple darts are all over the place. Therefore, that is not precise either. So the first one is not precise, not accurate. That is how most of us play darts, right? Not very good. The middle one with the pink darts, again, they all missed the bullseye. Therefore, it is not accurate. But they are all grouped up in the top right corner, so they are all very close to each other. The person who is throwing is very consistent, just consistently bad. Therefore, that person is precise, yet not accurate. Now, obviously, if you want to be a good dart player or precision sports, archer or shooter, then what you want to do is be both, which is the example on the bottom in green. They are accurate, they're hitting the bullseye, and they are precise because they are all grouped very closely together. That's accuracy and precision. Now, in science, we obviously would like to be both accurate and precise. Sometimes we're either one or the other, and occasionally we're neither, which is not good. So, to put it more in a mathematical context, which would be more relevant since we don't really play darts in chemistry, unfortunately, here's an example of 3 different students trying to take measurements. Notice they did 4 trials each. That's good in science. We don't do it just once. We do it multiple times. That gives us, again, like I said, more confidence in our precision or lack thereof. So student A did 4 measurements. You have the average. Student B, 4 measurements and an average, and the same thing for student C. We need to look at this and figure out which is the most accurate and who is the most precise and who is both or who is neither, okay? So it's a little hard to do it this way. I could talk you through it, but what I'm going to go ahead and do is just have it in bar graph form because it's so much easier to visualize. So on the left we have student A. Notice the true mass is shown in blue. The average is shown in purple, so their average is 10.13. The true mass was about 10, therefore they are not very accurate. Not horribly off, but not accurate. And you could tell by the discrepancies of the length of the bar graphs that they're really not precise. That is a very severe lack of precision. So that individual, student A, is not accurate or precise. If you look at student B, their average is well below the actual true mass, therefore they are not precise, or excuse me, not accurate, but their values are very close to each other. The bars are all very flat, very consistent, and all right close to their average. Therefore, they're pretty good and pretty precise, which means whatever they're doing, they're probably doing it wrong, but they're doing it wrong consistently, which, is good or bad. Now, it doesn't necessarily mean they're doing it wrong. It's just the values that they're using or measuring are consistently, those are wrong. Anyway, students see what we have over here. We have the average is dead close to the real mass, the true mass, and the precision is pretty spot on. So that student C is really good at being both accurate and precise. All right, another way we could compare the reproducibility or the confidence we have within a measurement is by calculating something called percent error. It basically is how far off are you or your measurement from the expected value. So it puts a numerical value on it. It gives us a percentage, so we could say we are off by 30%, which is not so good, or we are off by 2.5%, which sounds like a lot better, right? So, like it says here, the error is the difference between the experimental value, which we're just going to show as the capital E, and the accepted value, which is A. And then the equation is very simple. Percent error is basically the accepted minus experimental. The two vertical lines mean, oh gosh, I can't think of it, just popped out of my head. Basically, it means if you get a negative value, you drop off the negative value. Sorry, the name escapes my mind right now. But it basically means don't worry if it's a positive or negative. You're going to divide that number by your accepted value. And of course, to turn that decimal into a percentage, you would multiply by 100. That again will give you what's called percent error. So in this particular question here, it says there are 34 questions on a test. John has only answered 22 of them correctly. So what's his percent error? Not his grade, his percent error. So there's 34 questions. Again, that is the accepted value. There's 34 questions. There's no debating that. His experimental value is the 22 questions that he answered correctly. So we would take 34 minus 22, divide that number by 34, the accepted. That's going to give us a decimal, multiply by 100, and that would give us our actual percent error to show how far is John off from a 100. Okay? The next one says, the label says the rope is 2.15 feet long. John measures the rope to be 1.85 feet. So basically, how far off is he from actually being correct? Now, we could just subtract that and say, how far is he off? That's not what I mean. We want to find what percentage is he off, right? That's a little different. So, again, the accepted value would be the real value, 2.15 feet. The experimental would be what John was able to measure, which is 1.85. So we would do that as 2.15 minus 1.85. Again, that's going to be a positive value, but even if it was negative, don't worry. Divide that by the accepted, 2.15. That will give you a small decimal, multiplied by 100, and that will tell you the percentage that he is off from the actual value of 2.15 meters or feet. So that's called percent error. Again, both that and what we just talked about with precision and error are ways that we could communicate the reliability or our confidence within our experimental answers.